Всем привет. Я сзади, если что. Спасибо, что пришли. Я туда вперед не пролезу просто. Сегодня нас Alon расскажет нам немножко о TypeScript, я думаю, совсем немножко. В основном это будет доклад о том, как строить DSL, что это вообще такое и почему это круто. Alon будет рассказывать на английском, но он понимает по-русски.
Очень немножко, извиняюсь.
Нет, он понимает хорошо, но будет доклад на английском. Поприветствуйте Алона.
Привет. So hi guys, thank you for coming. You can go ahead. Okay, 1 second. So, it's almost 7 o'clock, a bit after, and you all had a pretty long day at work. Who of you would like to have a refreshing cup of coffee after the pizza? Raise your hand for a second. Okay, a couple of you. So, let's imagine that we have our very own coffee machine right here in the room. Even better, we have a barista. And you can walk up to him and ask him any kind of coffee that you like. You will probably walk up to him and say, "Hi, I would like to have an espresso." And he will say, "Okay, you want espresso?" He will go out the back, he will mess up with the coffee machine, and he will bring back an espresso. The entire process was really, really easy. All you have to say, one magic word, espresso. You didn't have to mention, "I would like to have a cup of water and 2 sugars and 1 milk." You only said one word, and he immediately understood what you meant. The entire process was easy because you had a common vocabulary with the barista. You have a common language with him. Even more, once you have established the common language with him, you can ask him, you can turn 1 cup of coffee into a multiple requirements of cup of coffees. Well, I'm here to tell you that we as developers can pretty much have the same process with our clients, with our teammates, with our colleagues by using DSLs. So now that we are all refreshed from this theoretical cup of coffee, let me introduce myself. My name is Alon. I've been working for Wix for 2.5 years now, and I'm developing Wix Stores, the e-commerce platform for Wix. I mainly develop using the Scala stack. Sometimes I do some other stuff, but I mainly develop in Scala. So let's talk about DSLs. The official definition of a DSL is, you can read it on the screen, but basically it's a specialized programming language to a particular application domain. Well, you might ask yourself, how is it different from any other programming language? Well, there are 2 main differences. The first one, DSL is targeted at a specific problem domain. The second one is it offers a higher level of abstraction to the user. What does it mean? When I'm using a DSL, I don't care about the underlying implementation of the code. I don't care about data structures. I don't care about memory usage. All I want to do is express my current solution to a problem in a specific small domain. With a general programming language, I can model everything and anything. With a DSL, I can model one thing, but in a much more expressive way. The fact that a DSLs contain nothing extra helps me focus on the problem I'm trying to solve. And finally, DSLs are made to fit their purpose only. So let's see a few examples of DSLs you might all know. The first one is the coffee DSL. I claim coffee is a DSL because it represents a problem to a particular, it represents a solution to a problem. The problem is how to make a cup of coffee. And the solution is by using these ingredients. We have our measurements like 1 cup, 1 teaspoon. We have our ingredients like skim milk, sugar, broad coffee. Using those ingredients and measurements, I can write recipes to make all sorts kinds of coffees. So this is a coffee DSL. The other one is SQL. SQL is a DSL that allows to query and manipulate data. And the last one I'm going to use is CSS. CSS is a DSL that allows us to define the looks and behavior of web and HTML components. So Okay, we've seen some example of DSLs, and if we go back to how we started and look back at the process we had with the barista, it's pretty much similar to the things we do in our day-to-day life. We get a requirement, a problem, and we're trying to find the simplest way to implement a solution. We're trying to basically to build a bridge from the problem domain to the solution implementation. Only the road from A to B is not always that easy. Why is it not that easy? Well, because of complexity. There are two types of complexity: an essential complexity and an accidental complexity. An essential complexity, this is the heart of the problem you're trying to solve. This is like the main issue you're trying to tackle. Whatever implementation detail you choose, whatever framework you select to work with, you cannot escape the fact that the problem you're trying to solve is hard. And accidental complexity, on the other hand, is something that we can control. This is something that we introduce to the code by the way we choose to implement something. Let's see a few examples. So, an essential complexity, like a really hard problem, is sending a rocket to space, building a search engine, supporting a high load of traffic. An accidental complexity depends on us, is writing unclear code, over-engineering stuff, or using the wrong tool for the job. Well, my claim is that if we use DSLs, we can reduce the accidental complexity of our code. Let's see a few basic examples. Here we see a test written in the JUnit framework. Nothing to do with TypeScript, don't go into details, just take a higher look at the test. It's really hard to understand what's going on. There are some asserts, some methods. Without going really into details, we won't understand it. On the other hand, look at the test that was written using Jasmine. Look at the DSL, how much it's almost like natural English. Expect hello world to be equal to hello world. I can show this test to any non-technical guy, and he will probably understand what I'm trying to do. He will probably understand what the author of the test is trying to assert. Well, I want to show you that if we implement these cells in our day-to-day jobs, we can have the same benefits in development. So let's try and during the next 25 minutes go through the process and build our very own DSL. Okay. So what DSL are we going to build? As I mentioned, I developed Wix Stores, the e-commerce platform. And when we developed the platform about 2.5 years ago, we needed to support a shipping model. Our platform allows users from all over the globe to build online stores. These online stores can, once users buy in those stores, need to ship their products all over the world. Every product they ship is shipped to another country, which has different shipping and tax rules. So when we needed to implement the solution in our platform, we chose some representation of some classes and functions. We wired them up all together, and we got a working solution, which is cool. But every now and then, when I need to go into the code and try to understand something or change something, it always takes me like 5 or 10 minutes just to get the hang of it. So I thought it would be cool, just for the presentation, to build a shopping cart text matching system using DSLs. And we're going to see like a really, really abstracted solution to this system. But I hope the process that I'm going to show you will be able to use it as well in your day-to-day jobs and implement and build DSLs that you find relative for your job. So let's imagine that we are building the platform from scratch. And we have a product meeting with the product guys. And they're saying, listen, I have these requirements, and I need you to provide a system that supports them. And as a product guy, he gives me the requirements in English. Basically, those requirements. For Canada, the tax should be 15% of the cart total. For the UK, the tax needs to be 12% of cart total, but when you calculate the tax, you should ignore the shipping cost. The third one, okay, for USA it's 7%, And when you calculate the tax, you should ignore the shipping cost and the discount. And the last one, the most complicated one, is for Finland, well, it's 5%, and you should ignore the tax only if the shipping cost is larger than 4 euros. So those are the requirements we got from the product guy. We as developers probably will think, okay, I need to translate them to some system requirements, something we can understand. And system requirements basically are the tax for a shopping cart is calculated by the shipping country. Tax is different for each country, and tax calculation is dependent on other factors like shipping and discount. At this point, we need to establish a common vocabulary. Like we and the barista could just say espresso, we need to do the same thing for our theoretical DSL. The benefits of a common vocabulary, if we establish one, will be clear communication between all product teams. When the QA guy will come to me, the developer, and say, listen, I have a bug regarding VAT or Brazilian tax, go to the marketing guy and ask him about it, we will all know immediately what we are talking about. I will not have to, like, it won't be a broken phone. We all know what does VAT mean. Another benefit is if we all speak the same languages, we can actually ask other people from other departments to come by and have a look at our tests, because the tests will speak the same language as the domain. So, for example, if we have a really complicated tax rule, which we as developer can implement, but we're not sure we understand all the logic of it because we need a domain expert to come and review it, we can actually show the test to the domain expert and ask him, are there any scenarios that we are missing? Are you not testing something right? Which is a really cool benefit as well. So let's try to take the English requirements and break it down to build our common vocabulary. First of all, we have the countries our system needs to support. The second one, we have several cart fields that we need to address. We have cart total, cart shipping, and discount. We have our verb. We need to ignore stuff when a certain condition applies. And we have a predicate in the last one. If a certain condition applies, then we need to do something. So, and finally, we have the tax percent themselves. So let's understand the relationship between the vocabulary we just broke down. Tax is calculated on a cart. Cart is shipped to a specific country, and cart might or might not have a discount. So, after we understood the domain, we created the common vocabulary, we built and we also described the abstractions, the relationship, it's time to actually implement them using code. So, for this lecture, I'm using a TypeScript. It doesn't have to be TypeScript, you can use any language, but just for the demo, it's TypeScript. And I will tell you in the end why I chose TypeScript on top of any other language. So, let's start with the cart, the cart abstraction. Cart is like a very, very, very basic abstraction of the cart we have in our shipping system. It has a total, which represents the total value of all the items in the cart. It has the shipping costs, it has the discount, and the country this cart is going to be shipped to. Notice that tax is not part of the cart. Tax is a product of cart calculation, something that we need to find. Another abstraction is basically just the countries we support. No need to go over it. USA, Finland, UK, and Canada. Okay. We're going to find a few relationships on the cart, a few functions. We have a cart field. A cart field is basically a simple function that takes in a cart and returns a number. All the cart fields we have, shipping, discount, and total, are just numbers. We have a cart predicate. A predicate is again a simple function that takes a cart and returns a boolean if a certain condition applies. We have tax calculator, which like tax calculator, this is going to be like the thing we are going to search all over this lecture, because it allows us to take a cart and actually return the tax for that cart. And the last one is country to text calculation is just a tuple that holds a country and the text calculator for that country. Those abstractions represent the things we saw before. The domain breakdown into a vocabulary. The vocabulary was built up into a relationship. And this abstraction represents the same things we saw before. So let's try and build our first line of DSL. This was the English requirements. For Canada, the text is 50%. So how do we start? Well, every DSL needs an entry point, something to start the entire process. For us, it will be the for function. The for function is a simple function called for. It takes in a parameter, a country parameter, and it returns a country container. A country container is a simple class that takes in its constructor a country, and it has a verb, take. Take, if you remember, is one of the vocabularies that is one of the words in the vocabulary we built before. Take is just another simple function that returns us a country to text calculation, a tuple which allows us to calculate the text for a specific country given a cart. Calculator is just a function from a cart to a number, and it does its logic by taking the cart total and multiplying by the text. Using these few classes, we can now support the following sentence. For Canada, the text is 15%. So the upper version is the English one, and this one is actually code in TypeScript. And we can actually see what's going on behind the hood. The for function, when we invoke it, returns a country container, which then we can invoke the take operator, the take method on it, give it a decimal which represents the text, and get a country to text calculation, which allows us basically again to calculate the text for a specific country. So the first one done, only 3 to go. We already support the first part of the sentence. For UK, the text is 12%. The question is, can we extend our solution to support the second part, ignore the shipping costs? Unfortunately, no, because by the time we finish evaluating the first part of the sentence, we are left with only a simple number. We can't extend our vocabulary using a simple number. So we will need to add an intermediate step. This is the old country container we just saw, which had the take method, and it used to get a text, return a country to text calculation. We now need to add another step, and instead of take returning a country to text calculation, which is like the final thing we are looking for, we are going to add a new object, text and country container. Text and country container, as you might guess, it's just a container which takes a country and a text. Here it is. Text and country container, just a container that takes a country and a text and is in its constructor. But once again, we are now expanding our vocabulary to a new verb. We now support the ignore verb. We can now ignore stuff. How do we ignore stuff? Really, really easily. When we return the country to text calculation, the calculator function will now simply ignore the count field which the ignore method takes. We take the count total, we minus the count, minus applying the count field function on the count, and then we just multiply it in the text. So using this, we can now almost done. Now we said we need to ignore stuff. What do we ignore? We ignore count fields. So let's define a few count fields. We have shipping and discount. Count field is just a function from count to a specific field. It's like a getter. It's nothing really, nothing special. Using these two, we can now support the following sentence. For the UK, take 12%, ignore shipping. Let's see what's going on there. So the first part is almost the same. We get a country container. We invoke the take method, and now we get a text and country container, which we pass on, which we call the ignore function on, the new verb we just added. We pass on the shipping field, and we get a country to text calculation. Cool. 2 done. Well, not quite, because if you remember the first sentence we supported, which was this one, when we were done evaluating it, we got a text and country container. But we need a country to text calculation, meaning the new step we added actually broke the first sentence we support. So we need to go back and fix it. How do we fix it? Well, this is something I want you to remember to the end of the lecture, because the fix is something I really don't like and it's really, really ugly. We're going to add some sort of like a converter method to calculate, which all it does is it skips the intermediate step we added before, and it just directly returns the country to text calculation. So now the DSL looks like this. For Canada, take 17 to calculate, which returns country to text calculation. In the end of the lecture, I'm going to speak about the to calculate function. So just remember it. Okay. So let's take a few short stops now and review what we've done so far. We broke the English requirements down. We understood the relationship. We created the domain abstractions. We implemented some logic. We broke some other logic. We went back and fixed it. Let's try to almost wrap it up and finish the last two sentences. So for USA, the tax is 12%. When you calculate the tax, you should ignore the shipping cost and the discount. Can we improve the ignore function to take multiple params? Well, we can try first by, instead of taking only one count field to ignore, we can change the parameter to a sequence, to an array, and take a multiple count fields. Our ignore function now needs to change as well, and instead of just doing minus, we need to accumulate all the count fields we are going to ignore. For that, we are going to use the reduce function on the count field, which is basically just runs on the count fields functions. For each one, applies the function on the count, adds all the fields, and in the end, just minuses, we're doing just count total minus count fields, multiply the text. Doesn't sum? Sorry? What do you mean? This one? But if I understood, applying, it doesn't sum. So I'm guessing I have a bug. Sorry about it. Okay. As I said, Scala developer still. Okay. So, but this is the idea. You change the parameter to a multiple one. You run it on over it. You sum up the values and minus the total. So now we can see it's something like this. For you say take 12%, ignore parentheses, discount, semicolon, shipping. It doesn't look that good. I think we can do a bit better than that. So to do a bit better than that, let's take it up to the next level. Up until now, shipping and discount were just simple function from a cart to a specific field inside the cart. We would like to describe a relationship between the cart fields. For that, we're going to add a new class called cart combinator. Cart combinator is basically just a class that takes a cart field, but it has a new verb again. It has a new word in our vocabulary again, the end. The end function takes two cart combinators and applies their logic to a new cart combinator, which allows us to do certain stuff. So let's see how the ignore function changed from before. Before, the ignore function just took a simple count field. Now it takes a count combinator, and it just does comb.count field with the count, and it's the same thing. So the logic of the function didn't change that much, but now it looks like this. For you say, take 12%, ignore discount and shipping, which is not much more English-like instead of the parentheses and the semicolon and stuff like that. So 3 down, and we have our last one to go. Let's just review what's going on there. So as you see, discount, the first part is the same we saw before. The second part, discount and shipping, using the new count combinators we described, and returns us a new count combinator with the logic of the two methods. And in the end of the calculation is country to text calculation. So that's what we support so far. Looks okay. We have one more to go until our theoretical system is done. We need to add the predicate. We need to support the if shipping cost larger than 4. So once again, as always, we are extending our language. We're going to go back to the count combinator, which now, and add the if method. The if method takes a predicate. And if this predicate applies, we return the count field. If it doesn't, we return 0. We also add a new method called greater, so we can describe the relationship. And using these two, this is the entire count combinator after the new function we just added. Now we have and, if, and greater. And we can support the following sentence. For Italy, take 15, ignore discount if shipping greater than 4. And as you imagine, this discount if shipping greater than 4, in the end, after we combine all the count combinators we defined, we get a new count combinator, which we pass back to the ignore function. And in the end, we get our country to text calculation. So this is the final DSL. This is how it looks like. Pretty cool. And we can compare it even to the English requirement that we got in the beginning. Just going to leave it in the screen for a few minutes, for a few seconds, so we can see almost like, I can bet you that if I take, I don't know, some guy from the street and show him the DSL and ask him, do you understand what it does? You probably say, what do you want from me? But after that, he would say yes. So, because this is like natural English. We all understand the verbs. We all understand the language. So let's see how we can finally apply this text rule to a count. So in theory, we will have some data structure like text rule DSLs, which will be a list of country to text calculator, which basically is the DSL we built before. We will have some function that will take a count and match the correct text rule by the country, just a simple match. And once we have the rule to be applied, we simply apply the rule on the count, and we get the text for count, which is the decimal, which is the actual text that we were looking for. So, if you remember in the beginning, I told you that once we've established the basic building blocks of the language, we can grow it to something more bigger and more expressive. Well, although we didn't have a requirement to the next slide, we can now support even this kind of stuff. For Finland, take 15, ignore shipping, discount if shipping greater than 4. And you can play around and expand it more and more and more. Because we build our building blocks correctly, every part can relate to a new part, and the logic can be combined. So let's talk about errors and exceptions. And although the DSL we just wrote and the code does seem like English, this is still code. And if it throws an exception or an error for some reason, the exception and the error needs still to be in the same domain-specific language. So if I, for some reason, encounter an array with size 0, I should throw no text was found instead of index out of bound. So the DSL of the user will still understand what's the context. And another important fact is the compiler acts as the policeman for you. The reason I choose to write it with TypeScript and not some, just vanilla JavaScript is because a lot of the logic we mapped and represented through our code and through the abstractions are enforced by the compiler. If you will try to apply a shipping rule to a text rule to some object which is not a count, the compiler will say, what are you doing? If you try to pass a predicate when it doesn't belong, the compiler will say, what are you doing? So a lot of the effort of the representation and the validity of the DSL and the business logic is already validated through the compiler. And because I almost finished, I would like to show you the same thing in Scala. So why do I want to show you the same thing in Scala? Because as you've seen, a DSL is just an abstraction on top of an existing programming language. And you are bound to the syntax and how much is the language syntax is agile, and you can play with it. So with TypeScript, we still had to keep all the parentheses stuff, all the dot stuff, and we still had to use the to calculate, the ugly function that I told you in the beginning. Well, in Scala, we have a few things that can solve it. So this is the DSL in TypeScript. This is the DSL in Scala. Which one is better? TypeScript. Pretty much the same, but syntactically, like for the I, the Scala one looks, in my opinion, a much more cleaner, much more like a sentence in English and not just method invocation one on top of another. So I want to show you, like in a few short minutes, why Scala is a good choice to implement DSLs and a few features of the Scala language. And first of all, it has flexible syntax fit for abstraction, meaning we don't have to keep the dots when we invoke new methods. We can just keep them. So the left side and the right side are equal. We don't have to use any semicolons. We don't have to use any parentheses. And we don't have to use type inference. And note that both the second one and the first one are the same in TypeScript. But the secret sauce of Scala is two things. One is the case class. Case class is like a really simple way to represent abstractions, because you can give, like, it's a small class with a few fields, but you can give them default values, and once you initiate the class, you can assign the values by name. So first equals Alon, last equals Muchnick is a much more expressive way, just other than name, Alon, semicolon, Muchnick. I can really express what I'm trying to initiate. And the really cool stuff is Scala implicits. Have any of you are familiar with this one, with implicits in Scala? Okay. So Scala implicits are basically a feature of the compiler, which allows us to do several stuff. Implicit conversion from type A to type B. They are statically typed, and they allow us to expand existing classes. So let's see what does it mean. Scala implicits are basically methods and parameters that are wired up implicitly by the Scala compiler without you having to specify this one should become this one. The Scala compiler looks at the signature of the functions, and if he finds inside his scope a function that converts A to B, he implicitly calls it. So let's see a few examples. The first one is implicit param. We have here say hello function, which takes an implicit greeting, and every print that I do with say hello will search for an implicit greeting inside its scope and will add it. So if I will have an implicit parameter somewhere else inside my code, the compiler will know by itself to put A and B in the same place. The Scala conversion. Okay, so if we have a function that accepts only int and we're trying to invoke it with int 1.1, the compiler will say type mismatch, expected int, actual double. But if I add an implicit conversion from double to int, the compiler will know to call this function to apply it, and the signature and the invocation of the int only method with 1.1 will be valid. So the same method can be applied to skip. If you remember the first step that we did, that we need to invoke the to calculate explicitly each time we wanted to use a simple shipping and simple text rule. In Scala, it's enough to define an implicit conversion, and so you can, if you go back to the first, if you go back to the first sentence, you see that for Canada, take 15% is allowed because we have somewhere in our code an implicit conversion from type country and text container to text and country calculator. So, final thoughts. Okay, getting the syntax done is hard. First of all, because maybe the verbs or the words you want to use in your DSL are already guarded words by the language. I couldn't use small for, and I had to use an if with a capital I, because those words are already in use by the language in TypeScript. So, and also trying to really express the way you think into code into a sentence is sometimes is a hard process. Like I think the hardest part of building this DSL was getting the first sentence done. Like writing for UK take 5. Okay, that sounds good. Another main point is a DSL needs only to be expressive enough for the user. What does it mean? Like in this example, in this presentation, we worked really, really hard to make the DSL as English-like as we could, because we assumed that the guys who's going to be using our DSL are some product guys or some business expert, and they don't understand code. But if you are a programmer and you're writing a DSL to start up an instance on Amazon, you don't have to be crazy and work so hard to remove the parentheses and put a dot there, because you know the guy who's going to be using your DSL is on the same level as you. So you can just like give him the abstraction he needs without working so hard for the syntax. And the last one is DSLs are really, really fun, because once you pass the first barrier and you have your first sentence, it's really fun to see how you can grow the language to new places. And that's it. Thank you. Any questions?
Hi. Thank you. Thank you for your presentation. It's really good. My question about beautiful code. Your code is really beautiful, and my question is, what's the difference between good code and bad DSL? Thank you.
A good code and a bad DSL? Well,
good code and good DSL.
And a good DSL.
And
so
bad code and bad DSL.
Actually, in the first presentation, I had an extra slide saying what's the difference between a good API and a good DSL. So the truth is there isn't a difference. Like if your user gets the abstraction he needs and it's comfortable for him to use the API you're providing, you don't need a DSL. You really don't, because the point of a DSL to make life easier for the user of it. So if you can provide a good enough API to the business expert who now needs to sit down and write 1,000 text rules, which one for each country, which has its own business logic, then you did a great job, really. But in that point, a DSL is a better solution. But if you have a simple code, like I'm pretty sure I can write this code in a simple classes and stuff like that. I did actually on the real system. So if it's a good API, I don't think there's a difference. I don't think you should even use a DSL, because there's a higher effort you need to put in to build it. But if the final user of the DSL is not a technical person, or is someone that you think that needs to get a better syntax or better abstractions, then you should try and use the DSL.
Sorry, perhaps I explained incorrectly. I mean, if I write some library with some API,
okay,
I can say that what I'm writing is a DSL.
Yeah, basically, yeah.
Or I should say that it's just a beautiful code. What you write, what you demonstrate on your slides, is it DSL, really DSL, or it's just a really beautiful code?
It's a DSL, because why is it DSL?
Why?
Because
my question, why it's a
because
DSL?
you can't use the stuff I wrote to represent stuff outside the business logic of the text rules, the domain. As I said before, my DSL is limited only to the scope of the text rules. I can't use the same DSL, the code I wrote, to do other stuff. So, and we do use DSLs all the time. If you use date objects, you can do like date plus 1 days. That's a DSL. You can say this is just a code to add one more day to the calendar, but this is a date DSL. So it's a very fine line. There's not like a Wikipedia definition. This is code, this is DSL. It's the way you think about it, the way you look at it. Life is DSL.
Thank you.
You're welcome. Okay. That's it? Okay.
I cannot.
No.
It's not actually a question. You just asked to make you remember about to calculate function, yeah?
And I said, the implicit in Scala solution, I didn't have to use it, if you remember. In the Scala solution, I just define an implicit conversion, and the compiler by itself knew to call this function, because the final calculation expected a country-to-text calculator. But without this explicit, I would have to tell the compiler how you convert this type to the final type. So that's why in the TypeScript I called the toCalculate, and in the Scala version I didn't have to do it. I only had to define an implicit conversion somewhere in my code.
Hi.
Hi.
So you just briefly mentioned you have to make your errors, like exceptions, in the same domain. Do you have a tips or like how? I think your slides was missing this part. Is it really hard? And what like maybe what you used in the real world to make it like human readable or whatever?
Basically, in our system, we just use case classes, the one I showed you. And the exception always, like in Scala, extends runtime exception, and the message itself, the whole idea of the exception of the error, is to be clear. I don't think it matters how you implement it, as long as the one who is viewing the exception understand what went wrong. So, yeah, sure. Yeah, like you test your code throwing an exception the same way you test your code is doing the right thing you want it to do. So you build the test up, some invalid state, you run the test, and you assert there was one exception with this type and this message, obviously.
I have a question. How do you actually decide that you need a DSL? So, for example, in your case, you can just build a map from the country to the lambda that accepts
the lambda, exactly. But who's writing this lambda? I, as a developer, have to write all this lambda for each country with its logic. Using this DSL, I can take my business dev guy and tell him, listen, this is the syntax. You're limited only to this syntax. If you are red, you're doing something wrong. And I think with a day or two, he can write his own stuff. He can build his own rules for each country. I don't have to do anything for it.
The actual problem I usually saw in that kind of stuff is that when you give not a developer, but some business guy, a DSL that is inside the language, he eventually gets to the error that he just cannot understand at all.
That's a good question, and it depends, I think, how good your DSL how good your DSL is, how good the BizDev guy is, and it's not for every situation. Yeah, that's it.
What about outside DSL? In the first slide, you display, you show us DSL with different syntaxes.
The DSL we just saw are called internal DSLs. Why are they called internal DSLs? Because, as I said, they are an abstraction, they are a higher abstraction on the same language. There are other type of DSLs called external DSLs. And external DSLs are a completely different animal, because with external DSLs, you just get some string, some text, and you need to parse the text first, understand the relationship between the text, and then pass on inside your code a structure that you can understand and parse, and from that deduct the actual logic. It's pretty similar to macros or something like that. So what we saw was an internal DSL, and if you just want to be able to write free text totally and send, then you have to parse the text, extract the tokens, extract the meaningful keywords, understand the relationship. Those are much harder to achieve. Mm-hmm. The same. For me, from the entire thing I showed you, the most meaningful one was static language types, because as I said, most of the logic of the business logic is already validated for you by the compiler. So if you have a statically typed language, you can write a DSL on it. You don't need some magic stuff like Scala implicits and stuff like that, or even flexible syntax. In my opinion, the most valuable thing is types, because that's what keeps you safe.
I will not agree with you. Ruby can do a lot of great DSLs, and it actually does, so it depends.
So I would like to see an example. Show me. Thanks.
A question?
Okay.
Yeah.
Thank you.
Too early. Are there any tools to help you to make these DSLs? Because it seems like creating all these crazy classes like country container, tax, and country container, blah, 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 is too much overhead for such a simple task like this.
Yeah. There are tools that you can use to actually parse external DSLs. You can get from Scala a few parsers to build text. Like in this example, I'm not familiar with, but I agree with you. This solution could be like much more simplified without using all these concrete types. Maybe a bit more lambdas and functions and stuff like that. But unfortunately, I'm not familiar with any like in-language tools that can help you generate all this stuff. Still.
Okay, it's time to applause.
Thank you, guys.